first of all, I'm very honoured to be here and getting to talk to you all. Thank you very much, Derek, for the invitation to come over to Cardiff and tell you a little bit about some of the work that I did when I was in Paul Callaghan's lab, and then how I've used that to launch a career in applying pulse gradient spin echo NMR to more complex systems to look at the transport in those systems. So my introduction to NMR came through Paul Callaghan. I was actually an undergraduate at Massey University when Yang Jia was there doing his PhD, and Yang and I have sort of vague memories of him teaching me physics in the undergraduate lab there. And of course, Paul Callaghan was my most dynamic physics professor, and so he got me, when I said I wanted to go to graduate school and I wanted to go to England, and I had sort of certain parameters about where I wanted to study, he said, well, why don't you go and do NMR, and gave me some names of some people that he knew to go and work with. And so I ended up going to University of Kent at Canterbury and doing my PhD, and I was working in the world of K-space at that time, looking at the way we could use oscillating gradients to look at, to maybe access more solid-like materials to do imaging, because at the time imaging was really only working really well in the body, on the liquid components, and so we used oscillating gradients, and our model for cartilage at the time was a piece of Lego. And so I imaged Lego and I imaged cartilage, and here you can see me during that time when I was at the University of Kent, relaxing while my finger was being imaged to look at, and this is my finger that you're looking at there. So this is the finger. Well, anyway, while I was over in the University of Kent, whenever I went to a conference and people heard my accent and realised that I came from New Zealand and wanted to talk to me about Paul Callaghan, and they immediately wanted to talk about this Q-space thing, and I didn't know what Q-space was. I was just learning about what K-space was. So after I finished my PhD, I went over to New Zealand to do a postdoc, and so this is the kind of my first introduction to the idea of Q-space, was some work that Andrew Coy, who was in Paul Callaghan's lab, had done using the idea of defining this idea of Q-space and the fact that we can look at the structure of porous media by looking at how the molecules move around inside that porous media. And so this was his data taking the Q-space domain of water diffusing amongst small polystyrene beads and the diffraction peak that occurred at the exact point you would expect based on the structure of the porous media. So I went over and worked in Paul Callaghan's lab for about 3 years. Here are some of the faces of people that have become really good friends, Elmer Fisher and Robin Dykstra, and then Mickey Kumlosh, who's working with Peter Basser now, and then also people like Melanie Britton, who's working in Birmingham, a professor there, and he again is Mickey. Now, it was a small research lab. There was often only 2 or 3 PhD students and postdocs combined, but it was a really rich environment in which to work, and was where I kind of got a lot of my education beyond my PhD that gave me the skills that I have used later on in my career. And it was a really rich environment because there were always people wanting to come down and work with Paul Callaghan and visit New Zealand. So Bernard Blumich and Charles Johnson, and then Ana Gill from Portugal were some of the faces that I saw as I spent time in that lab. So anyway, the idea of PGSE diffusion to measure diffusion and flow was really inspiring to me because of the correlation between Q-space and K-space, and the Fourier transform relationship that you could get. If you could get the relationship where you had very narrow pulses, then you would get this Fourier relationship between the displacement and the propagator of motion that Kaga had been talking about earlier. So here was the relationship that I became really fascinated with and enjoyed. The idea that the space in which we collect our experimental data, if you think of the combined effects in Q-space, so the area underneath the gradient pulse that you make a pair of, then you can Fourier transform this information. If you can collect enough data, you can Fourier transform it to get an entire representation of the propagator. And so that meant that there were a lot of really great fields in which we could apply this. If we could apply this narrow pulse gradient spin echo experiment, then of course you could look at the data in either domain and look at the attenuation of the data and get the diffusion coefficient, which was a result of the fact that what you were really observing was the width of the propagator in the propagator space. To make flow maps, as Yang had showed, then by thinking about the phase difference and the data that you acquired in your experimental space, then because you had basically a single, you were approximating it as a single delta function displacement in the propagator, then you could access the velocity. And then of course this was, you know, really beautiful if you start thinking about pipe flow. In the Poisson pipe flow, then you would have a completely uniform distribution of velocities when you're looking at things flowing in a pipe. And so the Fourier transform of this hat function is a sinc function, and so you could look at things like the minimum in your data as attenuation, and that could pull out things like the velocity that your fluids are moving. And these are things that even now are being used to make, and people who are working in low field NMR are often trying to look at the speed at which things are moving through pipes by just acquiring a few points in the Q-space domain and looking at where you get a minimum to try and find out where that velocity is. And of course, a lot of work at that time was, and is still being done now, the idea that if you allow a long enough observation time in your experimental data, then the molecules are able to sample the entire porous media, and you get diffraction minimums, diffraction features that are a function of the pore space that things are diffusing in. So just flick through these. So about that time, Joe Seymour came over. He'd been doing a postdoc earlier with Paul Callahan and had done some of the work that you might have seen from Paul Callahan that was done in Antarctica. And so I was working on a number of projects with Paul Callahan, but Joe Seymour waltzed into the lab and announced that we should measure the Taylor dispersion, phenomena that was well known in the engineering world that Joe was working in, measured Taylor dispersion using PGSE. And so he basically waltzed in and said, this is something that's going to be really easy to do. We're going to do it in one weekend. I'm heading off to Antarctica next week, but let's do this. And Paul said, sure. I think Sarah's got the skills to help you do it, so why don't you two just jump on and grab this data this weekend. So it turns out that about a year and a half later, that I actually managed to get that data. It wasn't quite as easy as Joe at first thought. And much of the challenge came with trying to find ourselves in the right time and space window that the PGSE experiment allows. But in the end we managed to get this data, and it was a really nice way to discuss the ideas between what you could observe in Q space and then where that came from based on the propagator. So we found a system. We used octane that was diffusing in 150 micron capillary. Octane had the right diffusive properties that it was able to sample this entire 150 micron capillary in the 2 seconds. That was really the maximum window that we had available to us with the PGSE experiment and the NMR system. And it also, we had to basically, the type of flow that we wanted resulted in us needing to basically use a 2 centimeter pressure head. So we couldn't have any, we tried to flow with water, then we would get small bubbles form in the water at the end of the capillary, and they would completely halt the flow. And so we ended up using octane in the end and just a 2 centimeter pressure head to make this flow. So anyway, some simulations by Birch. So at first we collected these propagators, and you can see that at the very short times, then even still we're getting not the hat function that you expect, but you're getting some convolution with the diffusion motion that's taking place inside the capillary. And then when we saw this, we thought potentially this was an artifact of the Fourier transform. But then simulations from Bertram Mance of molecules diffusing around in the same system and overlaid showed that it was a real feature. And essentially this is the basically an edge enhancement effect that you're getting at the edge of the tubes as the molecules are moving back to the walls and back into the flow again. So while I was there, also another project that Paul had me working on was the idea that, of course, that many people in the medical field were very interested in applying pulse gradient spin echo ideas to images and to looking at structures in biological tissues, but the limitation was that they didn't have, as many of you know, the strong gradients available to them. And so the idea was, can we get this structural information out? What happens if our pulses are no longer narrow, but we actually have finite gradient pulses? And so some of the work that I did with Paul, building off of work that Arvind Kaprahan had been coming up with an idea of using basically representing a finite gradient pulse as a whole lot of small narrow pulses with a time delay in between them. Paul's extension of that was to realize you could use matrix multiplication mathematics to model those processes. And so Paul had done that with narrow pulses, and he wanted me to take this and show that we could do it with finite pulses using this matrix multiplication method. And so the idea really was, what we showed was, if you take a narrow pulse or a finite pulse, then what you see is that the diffraction minimums are going to be reduced. So in other words, extended. So in other words, you're seeing larger pores effectively when you have finite pulses than what you would see if you measured them using the narrow pulse approximation. And the conceptual way of thinking about this is the idea that, there is some motion that takes place while you're applying your gradient pulses. If that motion is very small, then what you're essentially doing is measuring this displacement between where the molecules start and where they finish. And when you have a finite pulse on, then really what you're doing is your molecules are no longer located to the same small spatial location. Over the duration of the pulse, they're actually able to sample a larger region. And so the displacement that you end up measuring is going to be smaller, and so you don't get access to the entire space available, and so hence, as far as the experiment's concerned, you have smaller pores available to you. We also, in that same work, we went on and looked at the idea of wall relaxation, and wall relaxation was not such a problem with finite pulses, but in the narrow pulse approximation did the same idea. If you included wall relaxation, then you could get a misregistration of the size of the structure that you were trying to measure. And trying it out on different shapes as well, planar, cylindrical, and spherical shapes, then you can see that again, based on the sort of size of the pores, the point at which the diffraction minimum occurs is going to be different. So here it is registered to 1, and you can see it moving out from that point as we go to different shaped pores. And so really one of the conclusions that was made from that work was the idea that whether it's pore shape or wall relaxation or finite pulses, you have to be careful about having these effects there if you're going to apply them, because they all show modifications in the pore structure, the average pore structure that you find. Well, after working with Paul until about the year 2000, I moved over to New Mexico Resonance and worked with Ichi Fukushima and with Steve Altabelli, and continued the work that I'd been looking, I'd enjoyed this idea of collecting the full experimental data in the Q space and then Fourier transforming it and getting the propagators. And in some porous media there, we looked at gas diffusion as a way of increasing the time and space windows that you can get access to. And so finding a propane gas here that still had a decent relaxation time so that we could look out over a certain window in time, and then making use of the gas molecules that were diffusing faster, then we were able to look at the same diffraction minimums and 300 micron beads there. And so when you Fourier transform this data, you get the propagator measurement the result of the fact that the molecules are getting some restriction as they try to get out into their next pore. So here they are trapped in one pore, some are escaping to the next neighbor pore, and some are escaping into the third neighbor pore. Then the Fourier transform gives you a nice feature demonstrating the structure of that porous media. So after that, in 2001, we moved to Montana. Oh, I guess the part that I forgot to mention back there was that Joe Seymour became my husband. And so the two of us launched ourselves at Montana State University in 2001, and the research group has grown over the years. We've been lucky enough to have a lot of great people visit us there, I think probably primarily because of our location close to Yellowstone. So Janis Stepiznik and his wife and daughter visited us there in our very early days in about 2002. And anyway, also Josh Bray, who is somewhere right here and is in the audience today, he's now working at Nottingham after working with Melanie Britton at Birmingham. So I want to now talk about sort of the two applications. So as I said, I learned about Q-space imaging, Q-space ideas with Paul Callahan, and the propagator that you can get. And the propagator we looked at then was just simply water diffusing in a pipe. But since then, Joe and I have gone on to apply this same technique to a number of systems that are interesting to our collaborators and to sort of industrial applications. So one of the first applications we found ourselves applying the NMR propagator measurements to was the biofilm. The Centre for Biofilm Engineering is in Montana State University. It's one of the world's most renowned places to study biofilms. And so the idea with the biofilm, here's a number of biofilms that you can see. Here are some that we grew in our own lab that have been grown in sand. So it's the slime associated with the bacteria. The plaque on your teeth is another biofilm being laid down by bacteria as they settle on surfaces and put out an extracellular polymeric substance to support and protect themselves. Close to us in Yellowstone, we have beautiful biofilm mats created in the hot pool environment. And then over in Western Australia, you can see old stromatolites, which are essentially put out by bacteria as they pull in, create a composite from the material around them. So the biofilm, as many of you may know, is this idea that bacteria settle on a surface and they put out an extracellular polymeric substance, and this substance provides areas where they can live in a different metabolic state, as well as limits transport into the biofilm of things that might do them harm, and is also a way for them to control their nutrient supply. And so these are some of the sort of features. It's a very complicated structure-function relationship within the biofilm, but it is the natural environment that bacteria want to live in. So they're of course important because we want to prevent them in medical situations, but a lot of our colleagues that work with biofilms at Montana State are interested in them because they can be a helpful form of causing bioremediation by changing the state that contaminants are in so that they're no longer dangerous to the environment. So they're looking at trying to grow them in porous media. And so some of the first work we did was to come up with a easy to use porous media that fits inside the NMR system, so polystyrene beads. And we grew a biofilm within this polystyrene bead. And you can see that, you know, what they wanted to see was sort of images, because images help them understand things clearly. So here we can see that as the biofilm grows, the T2 relaxation down the bottom is reduced, and you can see that the biofilm's growing. But what we were demonstrating to them was that by looking at the fluid transport within these systems, you can get earlier access to the fact that there's biofilm contamination. And so although you can't see the biofilm over here at day 3, you can clearly see by the changed transport within the system, these are velocity maps, you can see that there is already blockages forming in this porous media, and that there's already a biofilm there. And then clearly by day 7, both the velocity maps and the T2 maps are showing this. But what we wanted to do was look at how we could use the propagator measurement to give us even more specifics about what was going on, more useful information about what was going on in the biofoul porous media. And the idea is, of course, that the dispersion, the diffusion changes as you have the porous media change. And so where we would get normal diffusion, Gaussian diffusion in a normal bead pack, as biofilm grows, you go to ideas of anomalous diffusion. And so these were the propagators that we obtained in the biofilm inside that bead pack. You can see here at day 1, after it's been seeded with the bacteria, but there's been no biofilm yet, that you get the normal propagator that you expect to see, Gaussian dispersion within this porous media. And then as we started to grow the biofilm, we see that we get some very large flows through the backbone of the porous media, as well as some trapped flow within the block pores within the porous media. And again, you can see these signatures here of the actual bead structure that the porous media that the molecules are in. And so that work finished with us applying fractional advection diffusion equations. Here's the data that comes from those models, and with the proposal being that the biofilm growing in a porous media could be modelled with fractional advection diffusion equations. So the second application that I want to share with you today, the idea of being able to measure colloidal particle motion. Of course, colloidal particles are really important as we think about industrial processing of emulsions, and also of biological systems where we have blood flow, and then of course contaminant issues in environmental situations is a really important application of colloidal transport. We weren't the first people to look at colloidal transport by any means. This work by John Tanner and Ed Steiskell. In the very early days, we're looking at restricted diffusion inside colloidal systems, looking at the way in which molecules move around those colloidal particles to get access to the restricted diffusion of those systems. So what we did was we sent a student over to Sweden to work with magnesium and learn how to make these particles. And we've been using these particles ever since in our lab. The idea about these particles is that you can get a hard PMMA shell, and inside them you can have one fluid that has a different NMR spectrum, NMR frequency from the surrounding fluid. And so in this particular case, it was an oil center and water is the solvent. And so we could spectrally resolve and look at both the colloidal particle transport as well as the transport of the solvent around it. These particles are fairly monodispersed, and so we can think of them as a model monodispersed hard sphere colloidal suspension. So here again is the propagators that we made of these particles, colloidal particles flowing inside narrow capillary. And what you see here is that the black solid line is what you would expect if you have water flowing through a capillary. You can see the average velocity inside the capillary, the maximum velocity, and then the convolution with the Gaussian diffusion inside that capillary. When we flow the colloidal particles through the system, we see that there's a slight deviation for the solvent versus the water when it's with no colloidal particles in it. So the blue is when we have water but with the colloidal particles. And that variation comes from the fact, and we can see this really clearly by looking at the oil signal. If we look at the oil signal and how it's moving, first of all, you see that oil has a lower diffusion. So the deviation from that sort of hat function or distribution of velocities is very small because of the reduced diffusion. And then the other feature that we see is that there's a clear increase in the oil signal towards the large higher velocities. And this is actually due to shear-induced diffusion across the capillary. And so these colloidal particles are centered more in the center of the flow. And you can see a corresponding decrease in the amount of water that's at the center of the flow. We've gone on to look at more complicated aspects of colloidal particle motion. This is an extension of the pulse gradient spin echo, and so we can go on and we can apply multiple pulses, and we can remove the coherent aspects and look only at the incoherent aspects of the motion by applying multiple gradient pulses. If we do that, then what we can start to get access to is some of the complex motion that's been proposed to be occurring in colloidal suspension flows. The idea that molecules can get trapped within cages and that there can be collective dynamics going on, and that at some sort of point in time a molecule will essentially escape its cage and move out into other parts of the flow. And so here we have measured the effect of diffusion over a wide range of times, and we've done that for a variety of flow rates. And what you can see happening by looking at just the first moment of that propagator, looking at the effect of diffusion, is that to start with, molecules showing restricted diffusion because the oil molecules are trapped within inside the colloidal particles, but at a certain point in time, depending on the flow rate, those molecules are going to essentially escape their cage and move out and see a higher dispersive motion due to the fact that they're moving out of that cage and moving into the and experiencing the main flow. So looking at that in the propagator space, we can see that so the blue ones are the ones after things escape from that cage. You can see that you're getting Gaussian propagators essentially returned to you. So I just wanted to give you a couple of examples of the way in which we're applying, the measurements of the propagators to other systems to tell us something about their complex motion. And I want to finish by just giving this quote that really captures, I think, how I feel about my journey from Paul Callahan's lab through to where I am now. A quote from Purcell in 1952. I remember in the winter of our first experiments just 7 years ago, looking on snow with new eyes. There the snow lay around my doorstep, great heaps of protons quietly processing in the Earth's magnetic field. To see the world for a moment as something rich and strange is the private reward of many a discovery. And I think this captures the fact that I feel like, right from the start, looking at octane molecules through till now where it's colloidal particles and biofilms, that one of the beauties of NMR and looking at diffusion NMR is that you're always imagining the dance scene that the molecules are performing. And I should thank my group and some of our funding sources, and thank you for your attention.